Hi, welcome to Lesson 5, Matter. Now, last time we talked about Kelvin and his heat death theory of, trying to figure out how old the Earth is. And we ran into the problem just around 1897, I think it was, when they discovered radioactivity and the fact that this radioactive decay in the Earth may very well be totally throwing off Kelvin's heat death calculations. So in fact, the Earth could really just be much older than his 20 to 40 million years. Now, I want you to understand radioactivity, but it's not that straightforward to understand meaningfully. I can say, it's alpha decay and certain types will be beta decay, and it really just is the number of neutrons, and that affects the isotope. But that's not very meaningful for you to understand really what's going on inside matter. So I think first we'll just go over briefly what matter is, and then more in depth what radioactivity is. So it helps to understand that in geology, we study matter at a variety of scales, right down to elements, atoms, and actually in some cases even subatomic particles have some indication in mineralogy. I'm no expert there, but we go right from there up to the scale of galaxies, our solar system. So this range and scale is enormous. It's vast, anyway, from the micro to the macro, to the beyond imagination. And in doing so, it's helpful to look at the sort of things we'll study. Like, for example, studying the solar system. We'll look at planets, their orbits, what sort of matter's out there, what elements. We'll look at the big picture of how rocks behave on Earth on the scale of a planet. Then we can go right in close, look at a mountainside, for example. You'll look at an outcrop and you'll see a particular type of rock. Say it's a sandstone. If you look a bit closer at that sandstone, you'll see that it's all individual grains of mineral crystals cemented together by various components. And if you look even closer than that, you'll see that these little tumbled, worn mineral crystals, in fact, have a structure within them. Yes, they're worn down, but their internal structure is still very ordered. For example, if it's quartz sand that's been made into this sandstone, that quartz crystal in there will actually have a very ordered atomic structure. And if you break it right down, you'll get to the individual crystal unit cell, which is just the smallest number of atoms that you can break up a mineral into and still actually be able to call it that mineral. Like, for example, quartz, silicon dioxide, silicon and 2 oxygens. If you took away 1 oxygen and just made it silicon oxide, I don't know if that would even be stable or whatever, but you couldn't call it quartz anymore at that point. It's something else. So that's the unit cell for all crystals. And they're essentially like geometric building blocks that can only be ordered in certain ways. And those ways manifest themselves in the shape of crystals we know, like pointed quartz crystals and cubic pyrite and cubic table salt, halite. So you can see that this order affects all scales of just the shapes and properties of things. Like when you build up those individual unit cells a bunch of times, creating different shaped crystals, that affects what wavelengths of light it absorbs and therefore its color. It affects whether it's see-through or if it's metallic looking. It affects how much it weighs and how hard it is, whether it's easy to break along cleavage planes or whether it's very resistant to breakage and hard to scratch. So we use all those things to determine what a mineral actually is. A mineral is, well, it's defined as a naturally occurring solid with a definite but not fixed chemical formula. I think I got that right. I might have to go back and change that because I always forget. But so that's what a mineral is. Quite simple. And if we go right back into what that is, like what are crystals made of? Like what are these atoms I keep mentioning? Do we really know what an atom is? I find the concept pretty difficult because you don't just see atoms in your everyday life. So in our eventual aim to understand radioactivity, let's take it right back down to the atom. Because ultimately that's what all this stuff, all the minerals, mountains, gases that we breathe, it's what it's all made of. So we have atoms. And an atom is a very small particle. In fact, it's got multiple particles to it. But it's a very small, indivisible element. And for example, you'll have an atom. There's a cloud of electrons on the outside. These are negatively charged, light little particles that zip around, or at least that's the sort of traditional model. And in the middle, there are all these other heavy particles, the nucleus, protons, and neutrons. The number of protons is essentially the element that we're looking at. So hydrogen, 1 proton, carbon, 6 protons, 7 is nitrogen, 8 is oxygen, and so on. And the properties kind of repeat themselves, and that's what, just periodically, and so that's why it's the periodic table by Mendeleev. Neutrons are in there as well, that's a whole other thing, and we'll get to that. I'm going to talk about this in more depth in the next lecture, but I just want you to sort of know where we're going. I'm sure that you've seen the traditional sort of bowling ball or billiard ball model of the atom, the Bohr model of the atom, with the red and blue little balls in the nucleus and electrons orbiting, zipping around out there. And that's great. It's the idea. But it's just a model, and it really breaks down when you're trying to explain atomic behavior in more depth than Bohr, who made this model, actually studied it in. Now we use a quantum atomic model, and that's a bit more complicated, and it's out of my depth, but the general idea is that the electron cloud is essentially indeterminate. You can't know where these electrons are zipping around. You can say, yes, there's a probability that they're in this shell, which is sort of like a waveform. But anyway, we know that we can figure out a probability, but we can't actually nail down where and how fast they're traveling. So you end up with a model of an atom that looks like the nucleus, and then sort of a fuzzy cloud. And the way you can think of it is, it's sort of like a drum head reverberating. and it'll make these constant patterns like a standing wave. That's essentially the idea, is that the electron cloud around an atom's nucleus is like a standing wave. That's not so important, and we'll go a little further into it. Anyway, so what I wanted to get across in this just introduction to the idea of what matter is just that it's not actually that straightforward. And it's been a real 300-year scientific journey and relay race to try and figure out these fundamental properties of matter. So just flippantly explaining, oh, it's radioactivity, I think it's a disservice to you. And it'll really help us out to go into a bit more depth and really sort of get why radioactivity was such an important concept in understanding the age of the Earth and the rest of the processes that occur on Earth. So we'll get into more depth on that in the next lecture.